like interesting developments since that time, right? And especially in the last 3 years, we see a lot of algorithms coming up, right? And so what we have done, what we will do today is we'll show you four algorithms from recent literature, try to explain it and also run it live so that you can have you can try to get the gist of it, right? As the rule that we try to follow is like nothing is only on the slide, but we'll also run it with you and show you how the results look. So for the next 60 minutes, the plan is to go through these four algorithms that I've picked, right? The first is the projected quantum kernels. So here the idea is rather than calculate the quantum kernel and measure the inner product similar to QSVM, we do something different. And we get into the details later, but this is the algorithm that was developed so that we avoid exponential concentration. The second algorithm is quantum reservoir computing. Here the idea is we want to do time forecasting, but here we are doing time series forecasting. But the pitch is that you don't do it, you don't circuit train, right? So you borrow the idea from classical reservoir, and so you have this quantum circuit as a reservoir, and but you avoid the circuit training part. The third is an optimization algorithm, which is the quantum enhanced MCMC, the Markov chain Monte Carlo, in which we have like quantum proposals, which lives inside the classical metabolic safety loop, right? And the fourth is another machine learning type algorithm where we have quantum Kolmogorov neural networks, which are learnable activation functions, which are built from QSVT, right? And so we'll show all of them on our platform, and we'll show like how they run as well. So coming to projected quantum kernels, right? And this is based on a paper by Huang et al. In Nature Communication, which is titled "Power of Data and Quantum Machine Learning," in which the idea is very simple, right? Because rather than trying to build kernels by hand, what we do is we do similar thing as QSVM, where we project each classical data into a quantum circuit, but then here the measurement is different, right? So what we try to do is we try to measure our quantum circuit in these three bases, right? X, Y, and Z, and we try to create a classical projection of of a quantum circuit, which is which is like a single qubit reduced density matrix, right? And so the idea is this what would this do is this will avoid the exponential quantum concentration problem that occurs in quantum kernels, right? The usually this problem occurs because as the qubit count scales, the Hilbert space gets quite bigger and bigger, and essentially you basically the matrix, the quantum kernel approaches identity, and therefore your SVM model is not able to classify anything. So the idea here is rather than do that, we measure every qubit in a quantum circuit through these three bases and create a reduced density matrix, right? And so there are some formulas. You can see that. So we create this row of k for x. So the row of k would be your qubit, the kth qubit, right? And so you create this for all qubits and for all data points. So you'll have this 3n kind of 3n kind of measurements that then again what you can do is then create the kernel yourself. So here what we're doing is here we're calculating the kernel ourselves, kpq, which is the projected kernel, which follows like an RBF kind of a formula. This is exactly the RBF kernel, right? But here instead of having these x, we have this reduced density matrix, and then we take the difference and square it. So it's like a Frobenius norm, right? And then we sum over all the qubits. So what we've basically done is uh, we have processed our classical data, converted into a quantum circuit, and then again projected back into classical space by measuring, and then we create a quantum kernel based on that. And so this is called like a projected quantum kernel, where you have this type of scenario. And so this what we have essentially done is try sidestep the exponential concentration problem, right? So some of let's go through some of the trade-offs and also the best practices, right? So the advantages, again, as I've been going on about, is the we avoid kernel concentration because Here we generalize instead of where the fidelity kernel flatlines. So essentially, what you would have seen when you try to scale QSVC to higher qubit counts, right? And so one other good point is the circuit runs. Since we only have three measurements for every qubit per point, so that's we have like O of n circuit runs instead of O of n squared, where we have like exponential number of circuits when we try to scale the data points, right? So here n would be the data point or the training point. Right? The third advantage, which is a different kind of thing, is like where we have no variational kind of circuit, right? So we don't try to train our circuit, other than we just try to add this kernel as a pre-processing step, right? Everything else remains the same, right? So there's the SVM step is convex before as well. So now that we also have that right now. So disadvantages like is I mean the disadvantage here comes from the data set, right? Because the way the paper tried to propose it, what they do in the original paper is they try to make a data set which is tailored to quantum circuits. So rather than so the claim for quantum advantage comes rather than the algorithm comes from the data set. So here usually what we see is the classical RBF. So if you don't have the pre-processing step, often ties it. So that's one thing we need to keep in mind, right? So if the classical RBF ties it, then this model is not something you want to try, right? And so another disadvantage is the short noise. Right? So short noise again is the thing that you would encounter when you try to measure something, but measuring it usually sometimes gives you the wrong result, right? And so where this kind of short noise uh, basically occurs in every kind of algorithm where you have to measure something, right? So here also again the same issue comes up because of the short noise. The kernel matrix may be different than the ideal one, and therefore if you want to be try to be accurate, you have to have like more counts, right? And then again, so this point is the feature map. So the feature map choice has always been heuristic in these kind of algorithms, and the PQK or the projected quantum kernel is no stranger to that, right? So we have this feature map that we require to embed our classical data to quantum circuit, right? And so this choice is usually heuristic, and so there is no principled recipe as to how you would want to do that. So it's usually the way we usually do is we have these predefined feature maps that we try to use. But yeah, you can also have your own feature maps, but there's no guarantee what kind of results you'll get. And so you're basically trying different stuff out to get good results, right? And so obviously there's some of the best practices that we have tried to uh, that to put here, right? So we already always want to test our algorithms on like state vector simulators before firsthand to see what kind of results we're getting, and then only we try to go to hardware. So but simulators usually have a limit of what kind of qubits count you can go to. So we usually start with a few number of qubits and then try to go for high number of qubits on the hardware, right? You don't want to run a small jobs on the hardware to waste hardware time, right? And then one thing to keep in mind is always start with like low repetitions. So repetitions is how many times you would like repeat your circuit, right? So you could always have high circuit depth. So instead, we suggest you start from like one repetition and then keep going on. But mind you that deeper circuits usually require more time and also incur more two qubit gate counts, right? And so again, so we also have these two parameters that we can choose, gamma and c, which are like classical parameters in the kernel. As we've seen before, these are like classical parameters, right? They don't enter the quantum part, so we can basically do cross validation or any kind of processing after that, which is usually free, right? So let's go to some of the parameters that we would basically try to look at. So this is based on our implementation on the platform. If you want to implement, you might have some different kind of parameters, but this is what we have chosen for our platform. So I'll just try to go through quickly, and we'll just go to the demo. Okay? So the qubit count is basically how many qubits you want in the circuit. So the way we have done it is if we have basically like one-to-one mapping. So one qubit would be one feature, But if you choose a lower qubit count, so what we do is we just PCA, so that dimensionality reduction from whatever the lowest is. So if you have a lower qubit count, we just PCA, and that's why sometimes you can use lower number of qubits. So then we have the feature map, so you can select between different types of feature maps. So we have like E2, which is like IQP style embedding. Then you also have the GZ feature map or the poly feature map, which is like a Qiskit based predefined feature maps that the Qiskit has defined, right? So we use those. Or also you can also have your own circuit that you can try, right? Then there's the circuit depth, which refers to repetitions. Then there's gamma, which is the RPF bandwidth that you can also check, and the C, which is the regularization for SVM. And then the shorts. So shorts would be how many times you run one circuit to get the expectation value, right? Let's just talk about what we can build, right? So obviously we can do binary classification, right? Since we have the kernel, we can do whatever with it. So there's binary classification, we can do multi-class, and then we can also do regression, right? We just put a SVR regression model instead of a SVM model, right? And then we should also talk about where should you try to use it and where not. So I think where it's best is where we have like a small number of data points, right? A tabular data sets, maybe at around 1,000 number of data points. That's where it will be like also quick and look good to look at. But yeah, again, so you would not want very large data sets where you have like images and stuff, because in that you have to try different types of feature embedding and so on, right? So let's just go to the platform and we'll try to run a very simple binary classification problem, right? So let me just change the sharing and we'll, yeah, hopefully everybody is able to see my screen. So I have the Bloq platform here. Uh, so I've already run some of the demos here, but we will go again. So let's give our demo a name and then say PQK, right? So we are trying to do a binary classification with the algorithm projected quantum kernel, right? So this is the data where you can select the data set. So this time around, I've generated a data set that we can use. So it's a synthetic data set of 200 points. So I've selected it. So if we go to the advanced options, you can see what kind of columns you have. So here it has 8 qubits, right? Sorry, 8 features. And then we have this column, right, which is the target. So here it is the label, right, which houses all the classes. Right, let's just select the whole data set. It only has 200 points. We can go all of them. Let's select, yeah. So all the qubits are selected, all the features are selected. Just say done. And then let's put 4 qubits. So since we have 8 features, but we have 4 qubits, what this will do is basically downscale your data set to 4 features so that we can have this one-to-one mapping between the features, right? And circuit depth here refers to the repetitions. Let's just keep everything default. Let's just and then yeah, let's try to run this. So once it starts running, you'll see that it's queued, right? So while this is being run, I'll just show you the results that I had that I've run earlier, right? So this is something what you would see as the results from a binary classification experiment, right? So we have the results where first thing you want to note is the accuracy, and the second thing we have also put is the Matthews correlation constant or coefficient, sorry, is which is the MCC, right? Which is like a robust kind of a metric to yeah to check your classification, right? And which is used when we have like imbalanced data sets, right? Where we might have one class which has like higher population than the other. So then there are also these other matrix that we can look at, but let's just look at the confusion matrix as well. So where we have the confusion matrix, where on the first column we have the actual labels, and on the first row we have predicted labels. And so you can see that 24 points that were from the zero class were predicted as zero, and then 14 from the one class were predicted as one. and the others you can see are incorrectly classified, right? So this is something you can do with all the classification experiment on the platform. You can check the metrics as well. I won't go through it, but you can also look at precision recall and so on for every class metric, right? So let's just see if it's completed. So you see that this model didn't perform as well uh, uh, for this kind of configuration. So the earlier configuration was a bit different. So it performed like 63% accuracy. But in this case, it's almost like random. So maybe what we could do is we could have a different kind set of parameters that might work well, right? Maybe this is because of the PCA that we did, or maybe the feature map, or maybe the number of shots. But yeah, so what you can do in this platform is experiment yourselves as to which set of parameters can work for your data set and a use case. Right. Let's go back to the presentation. So yeah, so what we saw was not a good result on the 4 qubit and the E2 feature map, which is like an IQP type feature map. And so obviously there's one feature that I didn't go through, but what you can do is rather than using the feature map that have been predefined by us, you can always try to create your own feature map using the Circuit Studio, right? So let's just move on quickly to the next algorithm, which would be the quantum reservoir computing, right? So this is a type of algorithm where we want to do some kind of forecasting or kind of regression, right? But it's mostly based for forecasting because we want to we usually have a time series, right? So quantum reservoir computing is like derived or like inspired from like a classical reservoir computing, right? Which is like echo state networks and so on, in which we have like a random dynamical system with some signal and then train the linear output that we get read out from its state, right? And so what we do in quantum reservoir computing is we replace that classical network with a quantum circuit, and which the quantum circuit is supposed to act like a high dimensional nonlinear reservoir, right? Where each window of its past value is encoded as a rotation angle. So the way we usually encode classical data into quantum circuits is try to use the rotation gates like RZ, RX, RY, and then try to embed that into the circuit, right? And so we have this circuit which is supposed to be like high dimensional entangled as well. So we entangle adjacent qubits, and then what we do is once we have this circuit, we try to we measure the z expectation of every qubit, and that becomes a feature for a classical regression model, right? So here there is no quantum circuit training, right? So there's no gating calculation for circuits. We just have the only trained component here would be the classical model that we input our quantum features to, right? So your H would be your historical window, right? Which is depending on the time window t, you would have a set of expectation values, right? And then you put it into a model, right, which can give you the forecasted values, right? So let's talk about the trade-offs and also again the disadvantages and also what things you should keep in mind, right? So the advantage is which is a big one is there's no circuit training, right? So therefore you have no gradients, you have no band plateaus, and so the only thing you train is a classical model, which is which we can do very quickly, right? And it's also easy to do. So another thing is that entanglement gives you like tries to give you the rich non-linear temporal features for free. I mean, for free is a bit bold, but the idea is that you have having the entanglement gives you like a rich Hilbert space, right? And so one big point I think should be highlighted is very cheap to run. You only have like one circuit per time window, right, or one point. So you can try to use this algorithm with bigger data sets as well. And so coming to the disadvantages, so the big thing I would say is would be the reservoir is random. Uh, Usually we have this feature quality depends on the downstream classical model, right? And so therefore, if we have a good classical model like ARIMA or ESM, they can basically be better in some cases when it comes to certain data sets or even certain runs. So your results might vary run to run, right? And so then there's also this idea of recursive forecasting, right? So the recursive forecasting, what it does is usually compounds error. So since the state of the reservoir depends on the previous state, right? So this have this dependency. So you can have this compounding effect where a small error can grow into something huge. Yeah, so that is the one thing you should look at, right? And so stop it before it grows and try a different model. Again, so the similar point to PQK here, since we're again trying to measure an expectation value, we would require high short counts to get a good result. Yeah, so lower short count would might basically hurt our expectation values and the feature metrics. Right. So the best practices for this algorithm would be to start low, as with all the algorithms. Start with small number of qubits and then try to go with higher historical windows, right? And then come back try to lower the window count, right? So usually why we say that is because with more qubits and short window, what we could have is the recursive forecast would blow up, right? So we have this compounding effect. Since we don't want that, we would want to try with a higher historical window and less amount of qubits, right? And so what we can also should do when we starting out is try to keep the forecast horizon short, right? So the forecast horizon here refers to how many points you want to, or how many steps you want to forecast, right? If you give it a high forecast amount, it might basically try to do something which is not required, right? And then again, as always with a lot of these Qualcomm algorithms, we always want to start with state vector simulation before we go on to the hardware. So again, this is the parameters that we have implemented. So this is, I mean, based on our implementation, and so we have qubits, which is the width of the reservoir, right? Then we have time window, so how many past steps we want to feed to each predictions, right? So which this also sets like the training sample counts. So too short and the regressor might overfit and give you bad results. So then we have horizon. So this is basically how many steps you want to predict, right? So I mean we again want to keep it small since we know the compounding effect can affect it. And then the device meaning what kind of simulator or hardware you want to run it. So we use air simulator as the default on our platform, but you can also select any kind of hardware if you want it, if you have the credentials and the access, right? And then finally we have shots. So how many shots you want to sample the expectation value, right? So let's talk about what we can build. So building is pretty straightforward, right? So as we talked about, we can do forecasting, and usually this forecasting is something like a time series forecasting, right? You can also do multi-step prediction, right? We are recursive build that is predicting multiple values, and then we have anomaly detection. So in this time, so anomaly detection would be like flagging points that deviate from forecast. So try to compare the forecast that you have with the forecast that quantum the algorithm has, and then we compare, try to get an anomalies, right? So let's also look at where it is useful and where it's not. So in this scenario, it will be useful when we have like univariate and normalized series, right? And with few hundred data points. Even though the circuit requirement for the algorithm is not much, it's order of it's linear, right? So it's order of n, but having like multiple thousands or even 100,000 points, it basically struggles. It has to do a lot of prediction, or it has a lot of training points, right? So if we have periodic or quasi-periodic signals, I think it can perform quite well. But if we have long horizon extrapolation or noise dominated areas, then it might not be able to. So if we have a little bit of noise, then it can uh, do well. It can try to do like something. It has like a denoising effect, right? So if you have a little bit of noise, you can get a forecast with no noise. But if you have too much noise, then the regression might basically push it overfit and then try to give you a result which has a bit of noise in it. Right? let's go to a demo, and then what we'll do is we'll try to uh, we'll have like a sine wave series, and we'll try to predict the output of that, right? So these are some parameters that we select. So two qubits, 15 has the historical window, and the forecast horizon is 2. Right. So let just go to the platform. So here we have the platform. Right. Let's just reset the thing, and let's go to the demo QRC. And so here you can select forecasting, right? Then we have QRC, and then let's select the sine wave that I've already uploaded. Let's just take a look at. Yeah, so you can see that continuous. So here we only see we have like one column, right, which is the value, which is basically a one-dimensional sine wave, right? So number of qubits 2. Let's go to the max 15, and let's keep it historical. The forecasting horizon as 2. And so simulating so device is where you would select devices if you have other devices selected, but right now we are using a simulator, right? So let's just run it, and so you see the experiment ID pop up as it's queued. You can see it's queued. Let's go to the results that I have earlier, right? So earlier I ran this, and so I got the training R2 or the squared error as 0.95. This is the training, and then test I got 0.55. And so the predicted values are 0 to 0.4 to 0.45. Let's see what we have got now. So okay, we got what we get now is like exactly the same as earlier. Basically, so training, you want your training R2 or R squared to be as close to 1. And if it's close to 1, that means it's perfect. If it's close to -1, then -1 or 0, it's basically not good, right? So you want it close to 1. So we've got 0.55, which is not the best, but not the worst as well, right? But you have to remember, we only kept it to 2 qubits. Yes, so if we selected maybe more qubits or so on, you might get good results, right? So also one thing I forgot to mention is the log. So you can see at what time or like when you started your experiment, at how many times it ran, and also when it completed. And so you can see it ran in like seconds, same as like earlier when I ran it. Right. So let's go to the presentation back again. Yeah. So what we did was we ran the ran the QRC for 2 qubits on the sine wave series what some at some parameters, and then we saw what was the result, right? So the result was not the best, but nothing. But yeah, so let's again go to the third algorithm that we want to look at is the quantum enhanced MCMC, or the quantum enhanced Markov chain Monte Carlo, right? So this is based on a very recent paper by Marshall et al. In which is titled "Quantum Proposals Inside the Classical Markov Chain Monte Carlo for Combinatorial Optimization." So this is a quantum optimization algorithm, right? So it's in some sense it's a hybrid quantum algorithm, right? Since it's like every algorithm that we see, it has a classical part and a quantum part as well. So in here, the idea is we want to solve icing or cubo problems, right? And what MCMC or QEMCMC tries to do is it has this warm started QAOA, right, which is the quadratic kind of solver QA circuit to propose the candidate bit strings, right? Inside a classical Metropolis Hastings loop with replicas at several temperatures and exchanging states, which is like parallel tempering. And so, what here the idea, the use or quantum computer is to make the move smarter. In some sense, is to sample from a probability distribution, right? Especially the Boltzmann distribution, right? And the classical acceptance rule, which is given by this formula here, the acceptance rules is what keeps the convergence guarantees, right? So we have this formula which determines if you want to switch from the string S to S prime, right? And so which is given by acceptance probability, right? So give where e here is the energy of that, or the cost of that string, right? And so this is your classical MC algorithm, but you, rather than doing using it to sample from probability distributions, what you used to do is you used to solve optimization problems which are post as QBO, right? So you have this quadratic binary optimization cost function which you use the Metropolis Hastings loop. And so the important point here is we have replicas, right? So rather than having the MC for like one temperature, what we do is we have these several temperature distributions which we sample from to try to get the best results. So the way we do it is a bit smart, right? In the sense that rather than having one temperature and then try to optimize that, try to loop through that, we have this multiple temperature states that which we switch between. So let's say we have temperature, let's say 0.01, temperature 1, and then temperature 2. So we, depending on the results, we would go across each one of them to try to find the bit string with has the lowest energy, and then keep this acceptance rules with us, right? So as the subtext says, each proposal we run a depth 2 QoA. So this is what the author chose for their algorithm, right? Which is seeded on the current change state. So what this means is we have this warm starter. So rather than starting from the zero state, what we do is we start from the this S state. So S state is your the current state, right? So warm starting here would refer to the fact that you start your QoA from the S state, and then we sample, and then we get the top k lowest candidates, right? So rather than looking at all the bit strings, we only look at the top k candidates, right? So let's go to some of the trade-offs and also advantages, right? So here the advantages is that we have the quantum proposal that can jump between distant low energy base and that random box can't reach. So what we usually want is we want a optimal bit string, right? So and when we say optimal, it's usually minimization. So if you want the lowest bit string, we want to choose lower temperature probability distributions. But what happens when the lower temperature distributions is usually your loop can get stuck into local minimas. So that's why if we have these on the proposals, basically we can have these jumps, right, which can give us advantage getting out of these local minimas, right? So again, and another advantage is the metropolis low discharge. So the MCMC convergence guarantees are still intact, since quantum doesn't enter the classical loop. We have like still the convergence guarantees that we get with MCMC, right? So another big advantage here is the parallel tempering, right? Because of the parallel tempering, we shake out of like local minimas on rugged landscapes. So if we don't have like smooth landscapes, right? If you have rugged landscapes, usually what can happen is we can get stuck into one of the local minimas and it's difficult to get out, right? So you think you might have gotten the result, but you haven't, and you have stuck into one of the local minimas, right? Let's come to some of the disadvantages that we see, right? So one thing is that this algorithm is kind of circuit hungry in some sense that it requires deep circuits with every execution. So we have one queue execution per chain per iteration, right? And so this cost goes fast, right? Because we have a lot of iterations as well, right? And then again, so the one thing that is usually uh, deal with quantum algorithms sometimes is that it is heuristic. So there's no proven speed up. So if you there might be cases where the classical MCMC with simulated annealing might be or like some uh, other kind of sampling, classical sampling algorithm might tie it. So like classical MCMC with some classical sampling, right? Also, one thing that this algorithm does is we basically have like fixed QoA angles that maybe might in some cases produce like random proposals. This is again related to the heuristic nature, right? So the heuristic nature is not only in the speed up but also on the results in some sense that we have this angles in QA like gamma and beta, which usually we optimize, but here there's no optimization. We just have it fixed, right? So if when they are fixed, you might sometimes you might have to tweak it if you're not getting the if you don't have the correct bit strings, right? So best practices is you want to have the temperature ladder geometrically, right? So we have the T low, which is the lowest energy for the distribution, and then we have the T high, where it's like the you should have it on the like a higher energy scale, right? So also need to watch out the per replica acceptance rates, right? So we need to uh, not go much higher to basically stop it from jumping everywhere around. So we should also aim to have these replica acceptance rate for around 20 to 40%, right? And in this case, we want to try to start our problem with like less than 10 variables. So less than 10 variables would be like 10 qubits. So in usually QoS and QoA, so we have like 1 qubit per variable, right? That's usually the cost Hamiltonian and the mixer Hamiltonian is designed. So 1 qubit per variable, and then what we can do is lower top k. So the k here refers to how greedy you want to be, right? So if you have a higher k, that means it's selecting a wide span of bit strings, right? And so if you raise it, you'll get more expression. If you lower it, you'll be like safe, right? You'll be stable. But if you have it higher, you basically are trying to opt for more exploration and try to see more solutions, right? And so some of these parameters that we have implemented onto our platform. Uh, so let me just go through it quickly. So replicas is how many parallel chains you want. So four is the default. So we have four different temperatures that the replicas will run. So then we have these low and high temperatures. So the ends of the tempering ladder. Actually, we have the temperature values in between to be defined like ourselves, which are like dramatically equal. But we can also but we have only given the low and the high temperature as the parameters, right? So the low will usually hunt for the optimum, whereas the high will look at the energy scale, right? And since the gamma beta, which are the angles for QAOA, right? And then we have iterations. So how many iterations you want per replica, right? Then the top K, which as I explained before, which is like how many low energy samples you want to kept per proposal, right? So the small is usually greedy, whereas large is usually exploratory, right? Then we have the swap interval, which is the steps between the replica exchange attempts. So how frequent you want to try to attempt an exchange, right? So how many times you want to, how frequent you want to switch your chains, right, between the different temperatures. And then we have shots. The shots would be how many samples you want to collect per circuit, right? So usually you want as many as top k, so enough to fill the top k. Since we otherwise it will just not select all the top ks, right? So it will be lower if we have lower shots than k, then we basically won't fill all the ks, right? So it has to be shots must be always greater than this k, right? So what we can build with it is so since it's a optimization algorithm, we can obviously try to solve optimization problems which are posed as QoS, right? And so this includes like any kind of max cut or scheduling or even portfolio selection. Only thing is you have to be able to write it as a QoS, which is the quadratic unconstrained binary optimization. And also talk about where you should use it and where you shouldn't. So where rugged energy landscapes where simulated annealing might not work. So it's good for rugged energy landscapes because it has the ability to go over local minimas, right? So that is a big plus point for QEMCMC. And then at least for today's simulators and hardware, you'd want to try to just limit up to 20 variables. I think that's what you can safely do on a 16 GB RAM. So if you can try to do higher variables as well, but your hardware might not be able to handle it. And then again, so you don't want to try for convex problems, right? So which have like exact solutions. Like classic solvers always win that one, right? So let's just try to run this on our platform. So we'll take a six variable icing problem, have four replicas, which go from 0.1 to 2, and then again, so which has like warm started proposals, some filtering, right? Let's just go to the platform directly. So here we are. Let's just go to the, so you have these two tabs on our platform, so machine learning and optimization. So you have to come to optimization if you want to try the QEM CMC, right? So let's just say one. You just select a cost function. So you can see you can write your own add your own cost functions using this program, right? But you can also, so I've also added a cost function that I've talked about, so which is yeah, which is this. And if you want to see it, so this is the cost function preview. If you scroll down, you can see this is the cost function that we're trying to optimize or minimize, right? Let's just close this. Let's select, and so yeah, so you can also select what you want to do. So what we'll do this time around is to minimize. So let's select. So we have bunch of algorithms that we can use, but we'll use the QEM CMC. Let's select the device. So we have a simulator, and then we have decided to have four replicas, right? Temperature 0.01. Let's select the high temperature to 2. We check if it is 2, and yeah, it is 2. And so we'll keep everything else the same. So gamma is the QA of angles, the iterations, how many iterations you want, top case, swap intervals. Let's just reduce the shots. Let's keep it around 256 so that it runs faster. And so then just run it. So let us see. So I've also run it earlier. So let us see. Yeah, it is queued. See. So let's just look at the results from a previous run, right? So this is what we see as the optimization results on the right side here. So we see the solution bit string, which is 00100, right? Which has six variables, right? You see the objective value, that is the value of the cubo, and then you also see the best icing energy, right? So this is the temperatures that we ran on. So 0.01, which was the lowest, and the 2 was the highest. And we also have these the two replicas that we didn't mention, but we had the 0.06 and 0.34, right? The solution again. This is like the metadata, and then you have this the energy convergence graph as well. So this will tell you. So from we had like 40 iterations, and then you can see that the cold energy, which is on the blue, right, and the hot is like the orange line. You see like the cold energy, like it's converges faster. It's like iteration 9. You can see the cold energy is like lower than the some for some reason hot energy basically tried to explore some other bit string, and so that raised its energy, and then again it converts back again around 10th iteration. So again, if you see that there are a lot of iterations where the energy is already convert basically, right? You can also view this in the full screen, so you'll see the data points and all the convergence in a big screen, right? So let's also look at the results what we have now. Oh, you can see that now the convergence is a bit different because of the random behavior of this uh, algorithm. You see that right now what happened is cold energy started from high energy point, whereas the hot energy had already converged onto the answer, right? So you can have this kind of behavior, right? Because again, you usually have a random behaviors for these kind of algorithms, right? Since it's heuristic based. But you can see that we also again got the same answer as the demo that I ran earlier, right? So this is the correct answer for this cubo, right? So let's just go back to our presentation and go on to the last algorithm for this session. Okay. So the last algorithm that we were to talk about in this session is the quantum Kolmogorov-Arnold network. So which was introduced by Avishkar et al. Right, in this archive paper that if you want to, you can check it. And it is a very interesting algorithm which is designed to be run on fault or hardware, right? So the idea for QCAN is based from again a classical point of view, right? So if you have the cans in classical neural networks as well, where the idea is in the classical cans is we flip the recipe for classical neural networks, right? Rather than having learnable functions on nodes, we have learnable weights on nodes. We have learnable functions that sit on edges, right? And where the idea is that the idea is based on the Kolmogorov-Arnold representation theorem, right? Which says that any function can be basically modeled by univariate functions, right? And so QCAN's move is that each X activation is like a Chebyshev expansion. So in this case, we're selecting on a type of function that we have decided, which is Chebyshev expansion, right? So that's how the authors in this paper have defined it. But in general, you can have any kind of function that you want to choose. But for this implementation of QCAN, the authors have chosen the Chebyshev expansion, right? And so the idea is we basically evaluate this Chebyshev expansion inside a quantum computer via quantum signal processing or QSVT on block encoded data, right? So if you see this expression that we have, right? So if you see the psi PQ, which is PQ here refers to a node P and the input node P and the output node Q. So for every node input output node combination, we have this expansion which is based on is based which consists of this TR, which is the Chebyshev polynomials of kind one, right? So the R is the degree of the Chebyshev polynomial, and so we evaluate this sum, which is based on the Chebyshev polynomial, to get this output of a node given an input degree and the weights WPQ, right? So what we do in this scan is rather than have a simple neural network with weights and fixed activation functions, right, like ReLU or any kind of activation function, we have a learnable function which sits on the edges, right, not on nodes, right? And so I don't want to go into the details, but this is the steps that Bloq code steps that we use to calculate the sum psi PQ, right, which is like the dilate, then Chebyshev, then we multiply this, then we combine, so we like sum, and then we collapse to get a single expression, right? Let's go to the trade-offs and the best practices, and also some disadvantages that we see. So one advantage, a very big one, I would say, is the parameter efficiency. So one Chebyshev weight factor per edge, the learnable activations are inspectable, right? So since we have such a small network, we get like very good, decent results based on the parameter count, right? And so the Chebyshev evaluation via QSVT, which is the quantum singular value transform, is exact and is not sampled from variation ansatz. So usually, with variation ansatz, we have a different kind of classical loop, but here the evaluation is exact and not heuristic, right? And so it's based on Bloq encoding, so it scales with fault tolerant hardware, right, rather than against it. So this advantage here is that we have fault tolerant based algorithm. So it'll only work well if when we have fault tolerance when we have fault tolerant computers where we because if you try to run this algorithm right now, what we will usually find is that the errors and the noise inside the quantum computer basically disrupts the whole algorithm, and we will not be able to get anything meaningful out of it. So today what we'll do is we'll run it on a state vector simulator, but since our platform has a capability to run on hardware, so as the new hardware comes out, fault tolerant kind of hardware comes out, we'll be able to run this algorithm there as well. So again, so since because we're limited to simulators, the network size or the practical network size is limited, right? Since like 20 qubits or 21 qubits is something one would usually be able to do on consumer hardware, but you can go higher if you have access to GPUs and higher quality hardware, right? And so this one thing is based on the gradient, since when we for the train for the weights, right? So we have to calculate the gradients And here the training training, which is based on SPSA, right? With simulated outputs like converge quite slowly because we are on a simulator, right? And so the best practices to keep in mind when trying to run this algorithm is to not first is to always the usually the general idea for best practices is to start slowly and then try to ramp up the parameters. So the first is to have the Chebyshev degree at 3 to 5, right? Since higher degrees might oscillate a little bit, right? Then you have again start with like small hidden layer. So again in this QCAN implementation, we usually have like 3 layers. It's like input layer, the hidden layer, and the output layer, right? So in our implementation, we've kept it that. So you can also remove the hidden layer. So you can again keep it to zero. Then you only have the input and the output, right? Again, we want to treat this as a research preview, and then like try to answer is what will we be running on when we have the hardware that can run this, right? So these are some of the parameters that we have implemented. Where hidden node is the width of the QCAN layer. Chebyshev degree is how much polymer order for each edge activation. So by default, it's kept at 3. But again, 3 is only for complex data sets, right? Loss function is how we want to train your objective, right? So we have cross entropy and squared error available right now. So then there's optimizer, which one you want for optimize this loss function. So we will use Atom, and then we also have SPSA, which uses less fewer evaluations, then epoch, so how many training passes you want, and then the learning rate, right? So what we can build with it. So we can, so since this is a neural network kind of model, we can build binary classification or multi-class, any kind of classification, and then we can also do regression, right? So any kind of smooth function fitting, which is the classical CAN habitat as well, right? Let's look at where it shines, where it doesn't. So small, again, so small tabular data sets and low dimensional function approximation would be something we want to look at. Again, so the issue here is that we don't have a way to run this on actual QPU set without having robust error correction or fault tolerance. So it's only limited to simulators, right? Let's look at what we'll do today. So today, what we'll do is on the platform, we'll run it on the same data set as we ran the projected called PQK on, and then we'll try to compare how the results were. Right? Let's go to the platform. Yeah. So let's just go to machine learning, binary classification, and let's select you can, and let's binary 8F. That's what we had. We had 8 features. Yep, this is all. I think we had 70/30. Let's just pick 70/30. Done. Then let's Let's have 4 qubits as we had earlier, hidden nodes let it be 4, epochs 10. This all looks good. Let's just run it. So again, I also had this algorithm ran earlier on the same similar data set, but with a lesser number of qubits. But yeah, the results were like I think decent, not that bad. So 0.70% accuracy. Let's take a look at the confusion matrix. So 20 of class 0 predicted correctly, 22 of class 1 predicted 1 correctly. So a little bit better performance on the 0 class. You can see that the recall for 0 is better, but the accuracy not so much. Let's wait for the recent demo so that we can compare with PQK as well. So PQK, I think, yeah, 45% accuracy, not that great. Let's see if QCAN can give us some better results. Let's see the timings. So yeah, so it took around a minute or so. So let's just wait till this finishes. Okay. So we see that, I mean, the accuracy is a little bit better than the projected quarter kernel, but by not so much. But here you see that the MCC is on the negative, which means that it's closer to random predictions, whereas here the MCC for QCAN is in like positive. So it's a little bit better, but yeah, not so much in case of the prediction. Okay, if you see the confusion matrix, you see that it's actually predicting a lot of zeros than ones. So it predicted like 26 plus 28, 28, which is like 62, so 64. So 64 zeros and predicted 1 6. So it basically has like somehow bias towards the zero label, right? So you'll see that for zero, the recall is 1, whereas the recall for class 1 is quite poor, 0.18, right? And conversely, the precision for zero is quite bad since it didn't get any of the lot of the ones as incorrect, but the precision for one is quite good. Right? So it predict whenever it predicted one, it predicted correctly, but when it predicted zero, it half the times it was wrong. Right? So we see that the QCAN wins in this classification like comparison. So let's just go back to the presentation and let's talk about bit about the platform and finish the session. Right? Yeah, so we ran the QCAN, also compared with PQK. So we saw that the PQK was a bit better in this scenario, so worse than for QCAN for this scenario. And so let's just review what we did today. All right, so we ran 4 algorithms on our platform, right? And so in which case we have these 3 features that we want to show to you, right? So the one first feature is the drop down, right? So today we didn't run the demos on actual hardware since the running on hardware usually takes a lot of time, right? You just want to keep it quick, but when you have uh, this drop down, you can easily select your QPU if you have access to it. So if you put your credentials, you'll be able to run algorithms on hardware with the click of a button, right? And then one thing that you can also do is have custom circuits. So if when we saw that for feature maps, right, you can have your own circuits that you and design yourself, and then which will be available on experiments for you to use, right? And also the full algorithm catalog. So if you didn't see, if you missed, there are a lot of algorithms that we have on our platform that you can try out very quickly. So these are like some of the algorithms that are there right now, but there are also more that we be adding every time something useful comes up, right? So let's go to, so these are like some of the plans that we have to for you to try out. So we have the standard, pro, teams and academia and enterprise. So again, we also have this 14-day trial. If you want, you can try to check out the experiments or the code editor, the circuit studio, right? So let's just try to end this session, and then we also have this QR code that you might want to try if you want to sign up for the platform. And then if there are some questions, you can always send it to this email, so nikhil.l@bloq.in, or if you have any queries about the platform, you can also contact the email at hello@bloq.in, right? So hello@bloq.in, so which is that HELLO@bloq.in for the access to the platform or also some questions. So I'll just pause a bit to if you have any questions. Otherwise, we can end the session. I'll
Nikhil,
put.
there are few questions in the Q&A.
Okay.
Yeah, if you look at the Q&A,
I can't see the. Where
it
is it?
near chat Q&A. If you go
I don't
to
see
the
it. I see the people. I see chat, but I don't see. Can you share it because I can't see it?
oh, it's a bit. Okay, let me
Maybe you can do
check.
like one or two. You can send it to me, and then
So you could see this. Can you see this? There is Q&A.
Are you sharing? Uh,
Yeah, I'm sharing the screen. You could
oh,
see.
let me stop. Let me stop sharing. Ah, okay. I see. I see. I see right now. Yeah, but I don't have that option on my. Oh
You can't see Q&A?
no, it's not on my
Okay,
thing.
sure. And then I can take questions from there. So Khalid ask, what encoding technique do we need to use when using QRC? What happens if we use around 15 or more qubits regarding the runtime? Can we use QRC for regression task?
Uh, I mean, okay, I'll go start with the last one, right? So you can use it for regression tasks, right? But usually it is best to use for time series data, right? But yeah, I mean, you can use it for any kind of regression tasks you want. And then the thing was about qubit time, right? 15
How
qubits.
much time will take for more than 15?
So 15 qubits usually you can, I mean, it's not that bad. So the time would be like every the usually you would not be limited by the time, but rather than the RAM. So 15 qubits is fine for like 8 GB, I think. So since QRC doesn't really require a lot of circuits, so the 15 qubit simulation for 8 GB should not take that much time. At max, like 5 minutes for like 100 points or something. So it's not really time hungry in that sense.
Nikhil, can
And
you see
the
the Q&A right now?
no, I can't see it.
Okay, okay, fine, fine. The first question was, what encoding technique do we need to use for
So the
QRC?
encoding technique, there is, I mean, there's no such of the encoding technique in general is usually the angle encoding, right? But the way we have implemented it right now on the platform is we have given a set amount of set like a fixed quantum circuit, right? Which is based on which has like a rotation and then entanglement gates as well. So, I mean, in general, you should be able to use any kind of encoding technique you want, like angle encoding or any type of encoding, but you have to make sure that it is not easy to simulate or it's like highly complex, right? Because you don't want something that is easily simulable using classical computers, right? So, in short, there is no like in general technique to encode. You can try any kind of techniques. You have like angle encoding, amplitude encoding, and so on, but you have to make sure that it is not classically simulable easily.
So regarding quantum enhanced MCMC, could you clarify where the primary mechanism for escaping deep local minima actually lives?
Um, so yeah, so usually the deep local minima usually happens at like lower temperatures, right? So when you have lower temperatures, you're trying to go for optimums, right? But the way you jump out of it is usually having in this scenario is having multiple replicas of the distribution at different temperatures, right? So the way we do it is we try to do this, as I said before, in parallel tempering. Right? So you want to have a different replicas at different temperatures, with which you can use to get out of this local minimas.
And then, is the quantum proposal circuit doing the heavy lifting by leveraging superposition to cross wide energy barriers globally, while the classical MCMC framework simply acts as a verification gatekeeper?
Yeah, the second part is right. So the classical MCMC is acting like a gatekeeper. You're right. So it decides when to switch and when to not. So when to switch the bit string or not. But I'm not sure about the first question about the superposition, because then usually in QoA, both the things actually work like so. Like special, what something special about quantum circuits is the superposition and entanglement, right? So in general, you cannot say it's just a superposition, but yeah, it's sure it's like one part of it. So yes, I'm sorry, I didn't get the question. What exactly is the?
He's asking, they're asking, is QAOA doing the heavy lifting while the classical
Okay, okay.
MCMC?
Heavy lifting, I guess you would say yes, in some sense because it is giving you the the proposals to come up with the answer, right? So it's trying to generate bit strings, right? So yes, I mean, you could say it's doing a certain amount of heavy lifting compared to classical MCMC.
So for the question about can we have access to documentation and Jupyter books? Yes, you would if you take access to Bloq platform. That is the only way you can get access to the node documentation and Jupyter books. Another person was like, "Have you estimated when these algorithms will surpass the classical one?" I can see a lot of progress, but still way behind classical.
Okay, I mean, yeah, so I would say that the currently thing that is limiting algorithms would be hardware, I would say. But yeah, I mean, there is usually right now we could see that for use cases that have like larger data sets and like the scale is very high, right? The classical still wins, but I think and I presume that once we have better hardware coming out, you start to see quantum algorithms try to compare with classical in a better way, right? Since we are limited to quantum hardware, which is like prone to noise, we're struggling to execute algorithms because of that.
Okay, I think we have. Let me see if there is any previous questions that I've missed. How to manage decoherence? I mean, I don't know what in what context it was asked 49 minutes ago.
I guess in case of like noise and stuff, I would say like noise in the circuit. Yeah, I mean decoherence is it's difficult to tackle by software or like by algorithms, but there are like mitigation techniques that you could try to use for that. But usually this is a hardware problem, right? Uh, and you could try to use mitigation. I mean, error mitigation would be the way to go if you want to try to tackle a decoherence. Or maybe also you could try to look at constructions where in which this decoherence doesn't like affect it. So something like cat qubits or something, I would say. But yeah, in general, this is like a hardware problem. But the best answer to it is having like some kind of error mitigation techniques to combat this.
I think one more question that could be the last question. What encoding technique do we need to use when using PQK?
So I mean, again, so this is again a heuristic. There is no right or wrong answer for this. You can try like any kind of encoding that you can find. So yeah, so in the paper, if you go through the original paper, they try to use like IQP style or like a ZZ feature map style encoding. But yeah, this is like an open research question again. So it's up to you as to what you want to try to use or what you can build yourself as well. Unfortunately, there is no recipe or fixed thing that we can do to have like the best feature map. Right? So it's always like activity research. We try to find what works for what kind of data set and so on.
Great. I think I hope there is no more questions. So would love to thank you all for joining the session. So if you want to get access to the platform, the notebook, the all these things, do fill this form out. I'm just posting it again on the Q&A. We'll be opening up to public soon, so you can always get it there, or you can fill this form that I put in Q&A to get access to platform. We would be happy to take and see if there is good researchers coming up from our platform. There are more features that we have on our platform, and it is going to come up very soon. So in the standard tier, you'll get 8 GB RAM,